Okay, in this video we're going to continue with exponential equations. It's going to be the second part of the dealing with exponential equations. We're going to deal with those we started in the previous one using this equation here, f of t equals a times b to the t power. We're going to expand that out when we do different types of compounding at different time increments. Okay, so we're going to change this equation to look like f of t equals a times 1 plus r over n, and then n and t in the numerator. So this is going to be our new equation. A is going to be the same value. B is going to equal this stuff here, 1 plus r over n, and n and t is going to be the power instead of just t, because we're going to do n times a year. So n equals the number of compounds per year. So if you're compounding yearly, then it's not going to change much. We're going to have f of t equals a times 1 plus the rate over, and t is going to be right here because n is 1. N equals 1. For yearly, quarterly, n is going to equal 4, so our function is going to change to this. A times 1 plus r over 4, and then we're going to write 4t here. So n equals 4. Daily, f of t equals a times 1 plus r over 365, because we're doing it 365 days a year, and then 365t will be our numerator, our power. Okay, so those are things that we're going to use. Now we're going to apply this to a couple problems here. Actually, one problem that we're going to use all these formulas with. It says we have $6,000 invested at an interest rate of 9% per year. Find the amounts in the bank in 5 years after we compound in different ways: annually, quarterly, monthly, and continuously. Okay, continuously is going to be where we have a formula that is, we'll do that one last. I'm going to write that below here, continuous model. We're going to do annually, quarterly, monthly first. Okay, so we're going to have our function f of t. We know it starts at $6,000. We're going to have 1 plus, our interest rate is 9%, so that's 0.09 here. That's always going to be the same. Our compounding annually is 1, so we're going to put t here, and that's going to be 5 in this fact. This is 5. So this is how much you would earn annually. Give us this number, and we just type it into our calculator to get the answer. 6,000 and 9 raised to the power of 5. We get $9,231.74. Since it's a dollar amount, we can go to that point. Okay, quarterly. We're going to change our function of, in this case, 5. I should put 5 up there. 6,000, 1 plus 0.09 to the quarterly, 4. And we're going to write 4 times 5 here. Or we're going to use the number 20 here for the power. Type that in to our calculator. get 9363.05. So $9,363.05. Okay, monthly. I didn't put a monthly one up above. Monthly would be every month, so that would happen compounding 12 times a year. So we would go 1 plus 0.09 divided by 12. And here we go 12 times 5, which would be, use the word number 60 here, because there's 60 payments there. 60 compounds. Okay, so we change that to 12 and change this to 60. I get $9,394.08. And all these I'm not rounding up. I'm always just keeping in the last cents because they're paying you. They're not going to round up. All right, now continuously is a different equation altogether. It modifies this equation because we've got to make this number huge. This number down here gets very big. Okay, this value right here gets very big, and so it's going to change to a constant number in actuality. There, so our continuous model, it's going to be f of t equals a times e to the k times t. All right, so this is going to be a constant. It's about 2.7. It's like a pi. It has a decimal, but it goes infinitely on forever and ever. Okay, and on your calculator, you should see an e to the x power on your calculator somewhere. And then if you put in e to the first power, you will get this decimal. All right, so we don't have an n anymore. We're just going to plug in these values. This k value is your constant growth rate. Constant growth rate. Okay, they're going to give you that value to you. Okay, so here's my last question. It is at, oh, I'm sorry, we didn't put this in and compute this one. I'm sorry, continuously. Let's go back and do our continuous model. Okay, so our continuous model would be $9% per year. So we don't have our constant growth rate on this one. So we would assume that it's going to be 9%, even though that's not a right assumption. Okay, so we're going to go constant growth rate. So it's 6,000 e to the 0.09 times 5, and we'll get an answer here. Okay, so we're going to type that in. I get 9,409.87. So each time the model increases our compounding, we get a little bit more money. Okay. All right, so we're going to do this last problem that has to do with constant growth model. Here it is. It wants to know when this function, this constant growth model with a 12,000 starting number, and we're growing at 17% constant growth rate, we want to know when it exceeds 3443. So we're solving an equation that looks like this. We want to know when this is greater than or is less than 12,000 e to the 0.17t. So we're going to need to know, we're going to need to plug this into a graphing calculator or graphing utility to figure this out. So I'm going to go back to the other problem set. We're going to go to Desmos to solve this. So we're going to type in y equals 12,000 e to the power of 0.17x, and we're going to type in the number y equals 3443. I believe those are two numbers. Let's just double check. 3443 at 12,007x. Yes, okay. So we're going to need to look to see where these intersect each other. So we're far away from this. We've got to go to 3443 up on the y-axis. So I'm going to have to zoom out a lot to get to 3443, because that's where it's going to be. There it is. There's 3443. Let's change our x-axis to just negative 100 to positive 100. Let's see what it looks like. Alright, I can see a little bit better what it looks like now. I left these the same so that we can see the y-axis. We're looking for this point right here. So basically it's going to be 6.2. Now if that's not accurate enough, we're going to need to zoom in on that point to get it to be closer. So I'm not sure if that's exactly accurate. I don't think it's within one decimal place, but we would need to zoom in on that section in order to get a closer approximation of what the answer is. So now I still have 6.2. So maybe I need to zoom in even more. Okay? So it's saying 6.2 is my answer, even if we're zooming in quite a bit. Well, let's try even more. So it's very close to 6.2. Very close. So I'm going to say the answer is going to be at 6.2 for this thing here, 6.2 years. So the answer here is 6.2 years later. Using Desmos to help me find that.